Hi, this is lecture 28 of Integrability 3. In last 3 sessions, what I have seen is the notion of integrability. Then I have said that is where we stop thinking about integrability. What we will have 3 more lectures to 3 more lectures for this week. In this 3 we will study the so called metric spaces. So till now whatever structure we have seen, continuous functions, differentiable functions, integrable functions, series, sequence, all these are based on the starting point of R. We have a set R, we have some addition, multiplication, the 2 maps, 2 inverse maps, and there is an order, then we said it is complete. So we said the complete order field is R. So with all these structures we have discussed the notion of differentiability, integration and all that. Now we will focus our attention not on R but an arbitrary set X with some structure. See, if it is only set, all the best thing we can do is think about maps between x to y or x to any other set. We put an extra structure on this that we are calling as a metric, and then study some maps between 2 metric spaces or some other relation. Now what is a metric? Metric is a map from the product to R, a map satisfying certain conditions. Do you know any map? See, I am saying that this is a generalization of whatever I have done till now. So if I take x is equal to R, so there should be a map from R class R to R, right. So do you know a map from R class R to R given 2 elements? Do you know how to produce the third element? Some nice structure that we have used again and again till now. What is it? If I take 2 elements, say x and y, in R we have used this modulus x minus y. This we have used multiple times. For example, when we are talking about convergence of a series, convergence of a sequence, we have used this, that given epsilon positive, the existence belongs to n, such that for every something we have an minus a is less than epsilon. So this modulus, see, this is what is this saying? This saying some relation between these 2 elements an and a. So this thing we have used multiple times till now. Now we are looking for a arbitrary set X and arbitrary map D. So firstly we cannot take any random map. This map dx is y is equal to modulus xy, this has some property. So some of those properties we will copy and ask that these maps is satisfied. So first property is the following. Suppose I take 2 elements x and y, d of xy should be non-negative. See, here we are talking about modulus function. So irrespective of what x minus y is, if I take corresponding modulus, the result is still non-negative. So this is what we want for every x comma y in x. And suppose you take x is equal to y here, then what is x minus y? X minus y is 0, modulus of 0 is 0. So if you take 2 elements that are equal, then d of xy is 0 here in this case. So we are asking the same thing here also. So d of xy is equal to 0 if x is equal to y. Suppose you take 2 elements x and y such that mod x minus y is equal to 0. What does it mean? Suppose x is greater than y. See, here we are in the set of R. So one can talk about greater than order. So suppose x is greater than y, then x minus y is positive. So modulus of that is the same thing as modulus of that is positive. It cannot be 0. but here we are asking it to be, so we are assuming that x and y are such that mod x minus y is equal to 0. So this cannot be the case. It can happen that x less than y. In this case, x minus y is less than 0. Modulus of that will still be less than 0. So in these two cases, we are getting that this is not equal to 0. Suppose we ask that this is equal to 0. We know the order property in R. For any two elements, either we have this property or this property when they are not equal. So when both of these fail, the only option that we have is x is equal to y. So that is what we will ask here. So dxy is equal to 0 if x is equal to y, this is straightforward. We are asking other condition also. If x is equal to y, if dx is equal to d of xy is equal to 0, then x is equal to y. Or you can put a extra f here and then say that for two elements x and y in x, dx is equal to 0 if and only if x is equal to y. So one can remove this. I have already put this condition here by adding extra f. Okay, IFF means it's if and only if condition, that is short form for the phrase if and only if. Okay, so this is the first condition. The second condition is the following. Look at this. Suppose you take two elements x and y, then you are considering the corresponding modulus of x minus y. It does not really matter whether you take x minus y or y minus x, because suppose x minus y, x is greater than y, then x minus y is positive, modulus of x minus y is equal to x minus y. Suppose you take y minus x, because x is greater than y minus x is less than 0, which implies modulus of y minus x is equal to minus of this. What is minus of that? Minus of y minus x is equal to x minus y. So it does not really matter whether you take x minus y or y minus x, the modulus is still same, it is x minus y always if x is greater than y. If x is less than y, whatever you take, it will be y minus x. So the second property is the same thing that we have discussed just now. For any two element x comma y in x, d of xy is same thing as d of yx, right. Now the third property I have used multiple times, but I didn't mention, I don't remember whether I have mentioned the name or not. So let me write down what is the property. Suppose I take two elements x and y in R, I mentioned this multiple times, minus x minus y, minus of x minus y, modulus of x minus y. Here I am adding and subtracting say other element z. So this is equal to x minus z plus z minus y. These two are same, I am not doing anything, I am just multiplying, adding and subtracting z. Then we have mentioned that if I consider this part, this is less than or equal to x minus z plus z minus y. So this is what we will be asking for the third property of the map D. What is it? D. So for three elements x, y and z, dxy less than or equal to dxz plus dzy. Let us ask that. So this is true for every x comma y in x. Third property is what? If I take three elements x, y, z in x, what we have is d of xy less than or equal to d of xz plus d of zy. Observe that for two elements x and y, d is giving an element in R. So here I can talk about their addition. I cannot talk about addition of two elements of x, I can talk about addition of images. So that is why plus makes sense here. Less than or equal to also makes sense, because this is element of R, this is element of R. So I can ask whether they are how they are related. So we are asking that they are related by this. So this is called triangle inequality. And this is also called triangle inequality, but we are dealing with a more general more general setup, not just set. So this is what a metric space is. A non-empty set. Whenever I write something, it should be non-empty. Otherwise, I will mention it that it is empty. So a set X with a map D from X to R, satisfying these three conditions, is called a metric space. Maybe I will rephrase it. So take a non-empty set X, then a map D from X to R. See, it is not to X, it is to R. For two elements of X, we are assigning an element of R. So for two elements of X, the assignment we are denoting by dx comma y, that is the notation. Now if this map satisfies these properties 1, 2, 3, which are not very surprising. All we are asking is whatever property satisfied by, some of the properties satisfied by this modulus, we are asking that for a random map from X to X to R. Then such map D is called a metric on X, and this pair is called a metric space. This pair is called a metric space. Okay. Now let us do some examples. See, in this course till now we didn't do many examples because you already know enough examples of continuous functions, differentiable functions, integrable functions, and you already know how to compute their integration and all that. But this is a new topic that I am assuming you have not seen this before. Even this term you have not seen this before. So that's why in these three sessions we'll try to do some examples. Maybe focus more on examples. Anyways, this you will learn maybe in the next course. This is only some introduction to. So maybe this I should be calling as introduction to metric spaces, not metric spaces. And it's only 3 sessions. You cannot cover much. If I say many things, you will not understand. It takes some time to digest, because this is new. Previously, the other ideas of continuity or differentiability, you have some idea what they are before. So for this we will spend some time, and we'll do it very slowly. There is no emergency. Now let us do some example. First example is already this, right? This keeping this as a reference point only, we have mentioned these properties. So at least this should be metric, and there is nothing to check. So that example 0, example number 0 is on R, the map D R cross R to R. See here, because x is equal to R, I am writing R cross R to R. If x is not R, it should be x cross x to R again. So what is it? If you take two elements a comma b, you are assigning it to modulus of a minus b. This setup is this is the matrix, and this thing is the metric space. Now another example, consider this R2, the so called Euclidean space. I don't want to use that word because that has some other meaning also, but take this R2 and define a map R2 cross R2 to R. Before I write something, you make a guess. You are dealing with this R2. This is how we write R2. You draw 2 lines and make them intersect at only one point. Then you declare that as R2. So now the question is the following: if I give 2 elements in R2, I want a real number. That's what a map D should look like. For 2 elements of R2, we want a element in R. So one such example is the following: you take x1 y1, x2 y2, and send it to. I will write something. You might already know what it is. So we are, for 2 elements, we are taking distance between them. What is it? It is under root x2 minus x1 square plus y2 minus y1 square. See, checking that this is a metric is also not very difficult. Whatever the result that we have, whatever the idea we have used here, one can use the same idea here, and then check for yourself that this map, the distance map, is a metric on R2. In general, you can take any n, and you can declare a map similarly. So, for any n, we have a metric space. Now, before we try to proceed for more examples, let us see what notions that I have discussed till now in those 27 lectures. How many of them can we copy paste to metric spaces? That's what we will do for maybe 10-15 minutes. Then we will do some example. Then we will stop the today's session. Next session we will do something else. So let us recall one by one. Initially, what we had is R has an order. Right, there is a separate map. What is it? It is a subset of R cross R with some conditions. Now, if I take X, and if I am taking a metric space X comma D, there is no special subset of X cross X. At least this is not coming from this set, this map, this structure D. So, arbitrary metric space may not have an order. It will it is not part of the definition of metric space. So, order in R is not transferred to arbitrary metric space. So, if I take two elements A comma B in R, one can talk about A less than B, B less than A, something like that. But in case of a metric space X with D, if I take two elements A comma B, I do not know what does it mean to say A less than B, because this structure is not part of the metric space structure. This D is only a map from X cross X to R, X cross X to R. See, you can of course take some arbitrary subset of X cross X and call it as a order, but it is not very clear why arbitrary subset of X cross X satisfy the order properties. Metric space can have order, but it is an extra structure. It is not coming from the metric space structure only. It is an extra structure. Now, so order need not be there in a arbitrary metric space given two elements. This does not make sense always. Now what? In case of R, we talked about bounded subsets, right? That was the first few ideas. So, a subset of R is said to be bounded if there is an element there exists say R belongs to R such that modulus of A less than or equal to R for every A belongs to A. Now, can I transfer this idea to a metric space? That is the question that we are trying to ask. So, does it make sense to talk about a bounded subset of a metric space? Now, how do I even think about writing like this? So, here we are asking for an element of R, not element of A, an element of R such that there is some relation between every element of A and R. That is what bounded subset mean. So, here we will do the same thing, a similar thing. We call A to be a bounded subset of X if there is an element R in X. Let me write down that R belongs to X such that modulus of A less than or equal to R for every A belongs to A. This is not really sensible because as I said, modulus of A, I do not know what does it really mean, and suppose even if it is element of A, I do not know what does it mean to say order. So, this is not a, this does not make sense. So let us not write this blatantly. Let us ask the following. See, observe here. Here, given element of A, we have an element of R, and this this extra relation is in R, and we are asking there is some element R belongs to R with this property. In case of arbitrary metric space, given element A belongs to A, I do not know how to relate the element in R. I do not know what is this. This is not there in for arbitrary metric space. What we have is, if I give two elements in A, not just one, but if I give two elements in A, then I know what is it? The distance is element of R. D of A comma B is an element in R. Now what I am asking is, instead of asking that R belongs to X, what I am asking is, there is a element R belongs to R, such that this element, the same idea, this element less than or equal to this for every A comma B. For every A comma B will not. See, observe the similarity. Here what we are asking is, a subset A of R is said to be bounded if there is element R belongs to R, such that for every A belongs to A, this real number, that is positive, less than or equal to R. Here what we are asking the similar thing, but in case of metric space, a single element of a metric space does not give an element of R. So for that what we do is, we take two elements of a metric space, then we can talk about the distance between them, D of A comma B. Then we are asking, there is a single element R belongs to R, such that D of A comma B less than or equal to R for every A comma B in A. This is what you are calling as bounded subset of metric space X comma D. See, here there is a suppose, see, D is just a map from X to R. One can ask that the image of this is bounded. This is a subset of R, right? D of X cross X is a subset of R. One can ask that this is a bounded subset of R. See, whether it is interesting or not, that is secondary question, but one can of course ask. In R we have a notion of boundedness. So this being subset of R, one can ask whether this is a bounded subset of R or not. If this is bounded subset of R, then we call D to be bounded matrix. In that case, any subset of X will be a bounded subset of R, subset of the metric space. Okay. Now what we will do is, this is about subsets of R. Then we talk about sequence in R. Sequence in R. What are these? These are just maps from N to R. So the same idea can be transferred to metric space also. So it is just a map from N to X. These are two sets. One can talk about map between them. So these are sequences in X. Now the question is, in here we have some notion of bounded sequences, convergence sequences, Cauchy sequences, monotone sequences, and all this we have. Do we have similar things for case of a sequence metric space also? So what is a convergence sequence in R? A sequence A from N to R is said to be convergent if there is element L belongs to R, such that some condition is satisfied. What is it? For reference positive, there is a N belongs to N, such that for every N greater than or equal to N, we have An minus L is less than epsilon. So here what we are doing is, An is an element of R, L is an element of R. Between those two elements we are assigning a real number, then we are asking that that real number is less than epsilon for a given epsilon positive. One can ask similar thing here. a sequence A in X is said to be convergent if there is an element L belongs to X such that some conditions is satisfied. What is it? Same thing, see, I said for two elements this modulus is giving element of R. Then using that we talked about we introduced the notion of a metric. So for two elements of X, the D of those elements is an element of R. There I can talk about this order property. So let us do that. So a sequence A in X, which is just a map from N to X, is said to be convergent if there is element L belongs to X satisfying the following property. What is it? Same thing, this is same as it is, this is also same as it is, such that for every n greater than or equal to n, what you have is the following. Here we are relating two elements of R by modulus. Here there is no modulus in X. What you have is distance d of an comma L is less than epsilon. This is what a convergence sequence in a metric space means. Now one can talk about a Cauchy sequence also. What is a Cauchy sequence? A sequence A is said to be Cauchy sequence if here there is no reference to any element of R. For epsilon positive there is a n belongs to n such that for every n comma m greater than or equal to n, what you have is modulus of an minus am is less than epsilon. One can ask same thing for a sequence in X also. What would be the corresponding change? Here instead of an minus am and modulus, we will ask d of an comma am. Let us write that down. So this sequence in X is said to be Cauchy if for epsilon positive there is n belongs to n such that for every n comma m greater than or equal to n, what you have is d of an comma am is less than epsilon. So this is about Cauchy sequence. You think about the bounded sequence also, that I am not writing here, I will mention in the lecture notes. So if it is first thing is to check is does it make sense, does bounded sequence in a metric space make sense? If it makes sense, what will be the corresponding notion? Here I mentioned for sequence is there is nothing to there is no surprise, it is just a map from N to R here, it is a map from N to X here. So then convergence sequence is also not very surprising. For two elements of R we are relating in the set of R by this modulus. Similarly for two elements of X we are relating them by D. Cauchy sequence is also no surprise. Now what did we do? After this we mentioned that in R Cauchy sequence is same thing as convergence sequence. In R. Now an obvious question to ask is here suppose I take a Cauchy sequence in X. Suppose I take a Cauchy sequence, then do I know if it is convergent? In case of R we had bounded subset of R, then we said the order, the extra structure that we have mentioned is special, so that we have the notion of supremum and infimum. Using this and something else we proved Cauchy sequence. Using this we proved there are nice elements in R. Using those special elements we proved Cauchy implies convergence for sequences in R. But in case of metric space there is no such extra information, it's only a map from X to R with certain conditions. That doesn't guarantee. See, if you see the definition, where is the definition? Yeah, if you see these three, there is no mention of extra element, existence of extra element. But in case of R, we have mentioned that the order is complete, which means what? For every bounded subset of R, supremum of X, supremum of that bounded above subset of R, supremum of that bounded subset is element of R. So there is supremum, there is infimum, and all that. So this phrase of there exists will have appeared many times in when we are dealing with R. That is part of the setup of R. R was a complete ordered field, the complete ordered field. So by the definition of R itself, it contains many there exist notions, at least one there exists notion. But in case of a metric space, that facility is not there. So given a metric space, you don't really know whether you can produce a new element from few elements in X, and it doesn't have any extra structure also. There is no addition, multiplication, nothing is there, only just one map from X to R. So it is not a smart idea, smart move to think that Cauchy implies convergence in a metric space, or try to prove that it is true. So let us postpone this idea of thinking about Cauchy, relating Cauchy and convergence in an arbitrary metric space. So let us come back to this maybe next session. Cauchy, convergence, how different are these in a metric space? This will come back to maybe in the next session. Now after this, what we have done is then we have focused on in case of R, we focus on continuous functions in R. So given a map F, we said F is continuous if some condition is satisfied. One of those conditions has something to do with convergence sequences in R. Suppose you take a element A belongs to U, for every sequence xn in U that converges to A, we should have fxn converges to fa. In that case, we said that this map F is continuous. One can do the same thing in case of metric space also. Here, see, starting point could be the following: you take the domain to be metric space, range to be just R, F from X to R is said to be a continuous function if given A belongs to U. See, it is only about convergence sequences. Convergence sequence makes sense in a metric space. So one can just take the definition: xn goes to A. For every sequence xn, for every sequence this xn in X that converges to this A, here it is not U, it is X. One can ask that f of xn converges to f of A. This thing is happening in X, this thing is happening in R. See, it is not really necessary to keep this to be R, you can take it to be any other metric space. See, it is only about convergence. Convergence is there in a arbitrary metric space, right? So one can take that definition. So X to Y, F, when I am writing X here, you should be thinking of this as X comma D, this Y should be thought of as Y comma D, or dx and dy. When if I am using D for both, there may be confusion, thinking that there is a single map that is metric for both X and Y. No, not that. There is a one map that is a metric for X, one map that is metric for Y. In this case, what we have is the following, that for every sequence given a element A belongs to X, for every sequence xn in X with xn goes to A, we should have fxn converges to f of A. Right, this is a sequence in Y, then one can talk about its convergence. Then I am asking that it should converge to f of A only, then we say it is a continuous function in metric space. Then what we have a alternative description for continuous functions. What was that? A function f from U to R is said to be continuous at an element A belongs to U if given epsilon positive there is a, what do we have? Do we have n or delta? We have a delta positive such that whenever Y is element of U with Y minus A less than delta, we should have Fy minus Fa less than epsilon. This idea can be transferred to metric spaces. So, f from x to y, as I said again, x here means the metric space x comma d, y here means y comma dy, here x comma dx. Now the same thing we will ask, given epsilon positive, there is a delta positive, such that whenever y, okay, here we did not mention about the fixing a belongs to x. So, after fixing a belongs to x, we say f is continuous at a if given epsilon positive, there is a delta positive, such that for every y in x with modulus between y and a should be replaced by d. D of y comma a less than delta implies d of fy and fa is less than epsilon. Now one thing is not very clear here. In case of R, the convergence is related to this idea. The notion of continuity using convergence is related to this idea, but in metric spaces I do not know whether it is true or not. So, check for yourself whether these two ideas are equivalent or not. If I take a function from x to y, there are two versions of continuity. One is using sequences in metric space, one is using this epsilon delta description in metric space. Are these two equivalent? That is the first thing that you should be checking. Then what we had the notion of uniform continuity, right? What is it? F from x to y. Okay, let me do the real part first. F from u to r is said to be uniformly continuous if, again there are two descriptions. One is if I take any two sequences, if their difference is converging to 0, then fxn minus fin should converge to 0. This is the description for uniform continuous functions where everything is in R. Let us try to do the same thing for arbitrary metric space. F from x to y is just a function where x and y are metric spaces with dx and dy. Then can I realize this in case of metric space? What is it? Sequences I know what is it. For every two sequences in x and yn in y, I do not know what does it mean to say this is going to 0 in metric space. Xn minus yn, you know, whenever I see this I should replace that with a d. So I will do that first. So d of xn comma yn, it is now a sequence. This is now sequence in R. Observe, for two elements in x, d of that is an element in R. So this thing is a sequence in R. So even though, see here, even though you might think that because the ranges are this thing is in R, then we are talking about the convergence. No. Here for two elements in x, this d is in R. So this sequence is in R. One can of course ask that this is converging to 0. There is no problem in that. Now one can ask the same thing here also. Whenever you have two sequences, xn in this is x and yn in x, such that dx and yn is going to 0. This is sequence going to 0. Then d of fxn fin, this is again a sequence, goes to 0. This is sequence in R again. The d of two elements of metric space lives in R. So this sequence is a sequence in R. So we can ask that this is going to 0. So let me say one more time. A function from x to y is said to be uniform continuous if for two sequences in metric space X such that this sequence in R given by the distance, now you can also put dx if you want, dx of x and yn, if this is going to 0, then we are asking that d of fx and fyn should also be going to 0. Now you should guess what I am going to do now. Next, we have sequence version for uniform continuity. You can write down the same thing for using epsilon delta description. Then you can ask, hey, are these two things same? That if I have a sequence, if I have a function between metric space that is uniform continuous using sequence version, is the same thing as using epsilon delta version. So one thing that I am not writing here is epsilon delta description of uniform continuity. After this you should check that metric space uniform continuous functions between metric space using sequence version is equivalent to epsilon delta version. You should check that these two are equivalent or not. I am not saying they are the same, I am not saying they are not same, I am asking you to check if they are same or not. So that is about uniform continuity. Then we had some results that relates continuous function with the uniform continuous function. See, if previously what we had is continuous functions are not uniform continuous every time. Maybe that is same case with the metric space also. There will be continuous functions that are not uniform continuous functions, and we have a result. What does it say? It says, suppose I take a map F from U to R that is continuous. If I have some condition on U, then I know it is U on R or the image, then I know it is uniform continuous. You recall what is the condition in case of R, then try to see whether you can extend that to metric spaces. What was U? U should be closed and bounded. This domain. So this thing makes sense in metric space also. Right? I mentioned about bounded subset in a metric space. What is it? Where did I write that? Yeah, here. A subset A of X is said to be bounded if there is a R belongs to R such that for any two elements of A, this thing is less than R. So bounded subset makes sense. So if I take arbitrary map F from X to Y, if I know, and this is already assumed to be continuous, if I know X is what does it mean to say X is bounded? Hey, X is subset of X, right? So I can ask that this being a bounded subset of X again. If X is bounded and closed, what is closed in case of R? One idea is, if I take any sequence in let me recall that for R, A subset of R is closed if I take any sequence in A that is convergent, the limit should be an element of A. The same idea can be transferred to metric space also. See, what is the problem? I am replacing R with X. Subset is subset, it is a set, so subset may make sense, and sequence makes sense in a metric space. So I am taking a sequence whose values are in A. Then convergence is, I already know what is the notion of convergence in metric space. This convergence to some element, then that element should be element of A. So closed and boundedness makes sense in a metric space. Now the question is, suppose I take a continuous function whose domain is closed and bounded, do I know that it is uniformly continuous? Try this. See, all this I'll many more details I'll add in the lecture notes, but before seeing that, you check by yourself whether you are able to prove continuous functions are uniform continuous if X is closed and bounded, or if it is true. See, we don't have many examples of metric spaces, that also I'll add in the lecture notes. We only have two examples. One is Rn R2 and R, yeah. So using the example that I am going to add in the lecture notes, you can check for yourself whether continuous functions is something as uniform continuous or not. Then after that what we have is the notion of that is all we have done for continuity. Then we talked about differentiability. What is it? Suppose I take a function f from u to r and element a belongs to, okay, before this a belongs to u, let me pause this. Before that we talked about limits. Limit also makes sense in metric space. See, even if I take any arbitrary function between metric spaces, this thing should make sense because this is only about sequences in R. This thing what we know till now is about sequence in R. So one can just transfer it to metric space also. Yeah, using this we talked about differentiability. So let us do that now. So a belongs to u. Then we have to talk about differentiability of f at a. We have this limit h goes to 0, f of a plus h minus f of a by h. Can I have a similar thing in case of what? Metric spaces. So first difficulty is the following. Here we are asking that adding some element of R to element of X. So I don't know what does it mean to say a plus X for a belongs to R and X belongs to X. I don't know what does it mean to say. I don't even know what should be the appropriate alternative. See, minus is okay. Minus I am replacing that by D, that is still okay for me. So I can write D of f of a plus h comma f of a, and by h also makes sense because this is a real number, so divided by h also makes sense. But the only problem is I don't know what does it mean to say plus. If there is a notion of plus in metric space, then maybe I can talk about differentiability also. But here it is not very clear what is plus here. So maybe we cannot talk about differentiability in metric space. Not in this sense at least. You can come up with a alternative notion, idea or something like that. But this doesn't seem to be transferred to metric spaces. This plus and all that. So differentiability may not be transferred to metric spaces. What about integration? Suppose I take a function f from a comma b to r. So we were talking about for integrable functions, these are bounded functions, right? So one can okay, if I want to copy paste that, one can ask that okay, I have a function f from x to y and it is bounded. What is bounded? F of x is a subset of y, and this is a metric space, so I can ask that this is a bounded subset of y, that is still fine. Now to talk about integrability, we need notion of supremum, infimum and all that. Do we have something similar in for arbitrary metric space? Just now I said it's not very clear what are the notation. So maybe integration also is not transferable to metric spaces, or maybe it's not straightforward how to transfer to metric space. So now what we have realized is whatever we have done in case of R, only sequence version and continuity can be transferred. So let us focus only on that. Whatever we can do, we will do just that, and nothing more than that. So that we will do in the next session. What we will do, we will talk about more details about sequences in metric space, their convergence, Cauchy sequences, convergence sequences in metric space, and monotone sequences. What about monotone sequences? That we have not mentioned, right? So what is monotone sequence? A from n to r is to be monotone if for every m comma n with m less than n, we should have am less than an. This is monotone increasing, similarly decreasing. See, unfortunately this idea of less than or equal to, see these are, suppose I am taking a sequence in x, for two elements of x there is no less than or equal to symbol or greater than or equal to symbol. So monotone sequences doesn't really make sense in a metric space, so that is out of question. So bounded sequence still makes sense because I know what is a bounded subset of metric space. this is still okay, Cauchy is also okay, convergence is also okay, monotone I do not know how to transfer it, because if I have to ask that some less than equal to symbol, I do not know how to put that in a metric space. So this I do not know how to do. If you know how to do, let me know, we will think about it. So yeah, that is about sequences in R being transferred to metric spaces. All these 3 ideas can be transferred. This is not very clear how to do, I do not know how to do that. Then about continuous functions, the definition is straightforward. So continuity using epsilon delta and also sequence version in metric space, it is I mentioned it already. Then about uniform continuous functions, then their relation between them. Then see, when we are talking about functions in R, we mentioned 2 more functions. What is it? Bounded and monotone. For same reason mentioned here, monotone may not make sense in case of metric space, but bounded should make sense. It is only about the image of the map. So this might still make sense, but this I do not know how to do it. So again the next thing to do is check relation between these 3 type of functions, and that is all. So in the process we will introduce some terminology depending on the necessity. So those terminology I am writing here now. So they are called connected, compact, complete. These 3 phrases, these 3 terms we will try to understand minimum extent. You will anyway see this in the next courses. So these 3 rough idea we will have some example. We will see how to use these ideas, and that is all. That is where we will stop thinking about metric spaces. Now 2 sessions are remaining. In those 2 we will talk about this and this. That is all for today's session. We will meet in the next session.